So section 10.4, we're going to be still working with radical expressions. We're going to be adding and subtracting them. So when you're adding and subtracting with radicals, there's one big thing to keep in mind, and you can think of this kind of like when you're adding terms together. So like when we have a 2x plus 3x, these are like terms because we have the same variable, they have the same exponent, but they might have different coefficients. Same kind of thing with radicals. We must have like radicals. And so what I mean by like radicals is that we have to have the same index, kind of like you have to have the same exponent here, and the same radicand. So the same thing inside of the radical symbol. So something like 2 square root of 5, kind of like going off of this one up here. 2 square root of 5 plus 3 square root of 5. If you think of those kind of like variables, the square root of 5s are the same. They have the same index, so the same number on the outside, and the same number inside the radical. So we can combine these together, and it'll be just like when you add variables. So remember, when you add variables, you keep that x, you add the coefficients. Same thing here, we're going to add the coefficients. So you add the 2 and the 3, keep the radical. So let's go ahead and go through some examples. And before we do that, actually, let's see why you cannot just add the radicands. So like we saw over here, we're going to be adding the coefficients, so we'll leave the radicand alone. So let's take a look at the square root of 9 plus the square root of 16 to see why we can't just add these together. Well, if I just added these together, 9 plus 16 is 25. The square root of 25 is 5. This is incorrect. So if we go ahead and go through the square root of 16 plus the square root of 9, doing this the correct way, remember order of operations, we do grouping symbols before we add. And so these square roots are just grouping symbols. They're kind of like parentheses, except these actually do something. They're an operation. So let's go ahead and simplify those first. So the square root of 9 is 3. The square root of 16 is 4. And 3 plus 4 is 7, not 5. So keep that in mind when you're going through these. You can't just add. Multiplication, you can. You can think of it like with multiplication, there's no operation in between, so there's nothing separating them. Addition and subtraction, you have to have like radicands like we have over here. All right, so let's look at some examples. And this is all we're doing in this section. We're just going to go through about 14 or so examples so that you can see some plenty of examples on this stuff. A lot of them are going to be really similar in terms of the process. I can't spell while I'm talking. So we're just going to look at a bunch so that you can see exactly how they work and a few different kind of difficulties with these. Okay, so we're told to add or subtract to simplify. So number 1 here, we're given 3 root 5, or 3 square root of 5, plus 7 square root of 5. So whenever you're adding, think like terms. They have to be like radicals. You want to make sure that your radicands and your index are the same. So here we have both of them are square roots, both of them are 5s. So we're going to go ahead and keep the square root of 5 and add the 3 and the 7. 3 plus 7 is 10. When you have like radicands, these are super fast. So let's go ahead and try another one. 2 square root of 7 minus 3 square root of 7. Again, make sure that your radicand and root are the same. We have the square root of 7 and square root of 7. We can combine. So let's go ahead and make sure you pay attention to if it's addition or subtraction. We have 2 minus 3, which gives us negative 1 square root of 7. Now, typically, I don't always write this 1 in here. You can write this as negative square root of 7, just like you do with variables, negative 1x versus negative x. They're the same thing. I do find the 1 to be a little bit more helpful when we get into some other problems here. It's really easy to forget that there's a 1 here. So if you think you're going to be forgetting it, I would just keep the 1 there. These are both perfectly acceptable answers. All right, number 3, given 2 square root of 11 plus 3 square root of 44. So for this one, if you notice, we do not have like radicands. We have an 11 and a 44. We can make these look the same though. And in order to do that, we're going to simplify. So sometimes you'll simplify and your radicands still will not be the same. That just means you can't simplify. But most of the time, if they're giving you ones like this to simplify, you usually can. So let's go ahead and look at these. 11 is prime, which means that we can't change that 11. We can't reduce it down, so let's leave that. But we can simplify the 3 square root of 44. So for this one, remember what we're going to do is I'm going to put this over here and we'll kind of work on it here and then bring it down. So we want to split this 44 into a perfect square times some other number. And for these, it's actually really helpful to look at your other square roots and see what you have there. See how we have an 11. So our goal is to make these match. And 11 does go into 44 4 times. 4 is a perfect square, so this is what we want to use. So we're going to have 11 times 4. And now if we go ahead and take that 4, or the square root of 4, out in front as a 2, so square root of 4 is 2, leave this one alone for now. And now remember, whenever you take something out, you're going to multiply it by what's in front. So we're going to have 3 times 2 in the front, and then just an 11 left on the inside. And now let's go ahead and multiply these before we add. Always do multiplication first. So we have 2 square root of 11 plus 3 times 2 is 6 square root of 11. And now that we have like radicands, we have an 11 and an 11. We can add our coefficients. So we have 2 plus 6 is 8 square root of 11. That one was a little bit longer, but that's typically kind of how they'll look. You'll have to simplify the radicals down. If you can make them the same, then you can go ahead and add them together. So let's go ahead and try another one. And I'm just going to put this one. Well, let's go ahead and do it over here. So number 4, we're given 5 square root of 12y plus 6 square root of 75y. So first thing to identify here, we do not have like radicals. So we have a 12y and a 75y. We want to make those look the same if we can. You can't just magically make them look the same. We want to go ahead and simplify. So if we look at this 12 in the front first, that's not a perfect square, but I can split it up so that it's the product of a perfect square and some other number. So we'll leave the 5 in the front, and then 12 is divisible by 4. So we're going to write this as 4 times 3, leave the y. Now our second radical here, leave the 6 in the front. And what perfect square goes into 75? Well, 25 goes into it 3 times. Notice how what we're left with on the left radical is a 3y. What we're left with here is a 3y. So you can kind of use that 3 that we had left in that first radical as a hint for this one. Now we can go ahead and take things out. So the square root of 4 is 2, so we'll take a 2 out. On the right side, we're going to have the square root of 25 is 5. And now remember for the y's, you can only take them out if the exponent is at least as big as the index. Because the index here is a 2, it's the square root, and we only have one y, we can't take any out. So let's go ahead and just take out our numbers. So we're going to have a 5, whoops. 5 times the 2 that we took out, and then we're left with a 3y, plus 6 times the 5 we're taking out, left with the 3y. 5 times 2, so we're going to multiply now, we get 10 square root of 3y, plus 6 times 5 is 30 square root of 3y. Now you can see that we have a 3y and a 3y. They're both under square roots. So we can go ahead and add those coefficients. 10 plus 30 is 40 square root of 3y. All right. Let's go ahead and try some more. Number 5. We're given 9 square root of 5 minus 4 square root of 10. Now for this one, if we look at this 5, so right now we don't have like radicands. 5 is prime, so we can't break that one down. And if we look at this 10, we can do 1 times 10, 2 times 5, and that's all that goes into 10. Now, besides the 1, which doesn't help us break it down any further, there are no perfect squares that go into 10. So since this 10 cannot be broken down, we can't simplify this, which means we can't make those radicands the same. So we cannot simplify this. So you're either going to say cannot simplify or already simplified. Either way, we can't combine those. Number 6, we're given 3 square root of 8 minus 6 square root of 50 plus 2 square root of 200. Now this one's a little bit longer, and right now we have an 8, a 50, and a 200. None of those are the same. So first thing we want to do is see if we can break these down. So we're still looking at square roots, so a perfect square that goes into 8 is 4. So I'm going to break this 8 into 4 times 2. If we go ahead and look at the 50, notice how in this first square root, the thing that's going to be left on the inside is the 2. Well, 2 goes into 50 25 times, and 25 is a perfect square. So that's the one we want to work with, 25 times 2. And if we look at this 200, 2 goes into 200 100 times, and 100 is a perfect square. So notice how we broke all of those into some perfect square times 2. So you can use that first one as kind of like a hint for the others, assuming they are able to be written as like radicals. Now we can go ahead and take stuff out. So the square root of 4 is going to come out as a 2. The square root of 25 will come out as a 5. And the square root of 100 will come out as a 10. So now remember, we're going to be multiplying the number out in front by the number we're taking out. Leave that 2 on the inside. Minus 6 times 5 is 30. Leave that 2. Plus 2 times 10. Leave the 2 on the inside. So those are the numbers we took out. We took out a 2, oh, sorry. I got ahead of myself on that middle term. 6 times 5, so we took out a 5. Then we took out a 10 here. You can multiply straight away like I did here. You will probably get it eventually in the habit of doing that. Until then, if you want to do it like this to remember that you multiply them, that's also a really good idea. So now let's multiply. So 3 times 2 is 6, root 2, minus 6 times 5 is 30, root 2. plus 2 times 10 is 20 root 2. Now they are all root 2, so we can combine all three of these coefficients, just like if you had three like terms. So 6 minus 30 is negative 24, and negative 24 plus 20 is negative 4, and then square root of 2. Okay, let's go ahead and try, we'll do one more on this page and I'll get a new page up. So they're gonna start getting a little trickier after this one. We're gonna start introducing some variables pretty soon. So number 7 here, we're given 7 cube root of 81 plus 3 cube root of 24. So right now we have a like index because they're both cube roots, but we don't have like radicands. And so I'm actually going to focus on this smaller number first to kind of use that as a hint for the other one. So if I go ahead and look at the factors of 24, we have 1 and 24, 2 and 12, 3 and 8, 4 and 6. And we're looking for a perfect cube that goes into this. That's going to be 3 and 8. So I can go ahead and rewrite this one as 3 cube root of 3 times 8. Now, if I go ahead and look at the other one we have here, the one that's going to be left on the inside, we can take the cube root of 8. So we're going to be taking that out. The 3 is going to be left on the inside. So let's see how many times 3 goes into 81. So you can always kind of divide this. So 3 goes into 8 twice. So we get 27. So in order to get 81, we can do 3 times 27. And 27 is a perfect cube. 27 is 3 cubed. So let's go ahead and change this 81 to a 3 times 27. And now if we go ahead and simplify, we can go ahead and take out the cube root of 27. So the cube root of 27 is 3. And the cube root of 8, which is 2. So now, just like we did before, we're going to bring those numbers in front and multiply. So we'll have 7 times 3 times the cube root of 3 plus 3 times 2 cube root of 3. So 7 times 3 is 21 cube root of 3 plus 3 times 2 is 6 cube root of 3. And we have like radicands and indices. So then we have 21 plus 6, which is 27 cube root of 3. So this is going to work exactly the same for fourth roots, fifth roots. As long as your index is the same and you can make them like radicals, you can add them together. All right, now let's go ahead and try. Let's go ahead and do a fourth root so you guys can see one. So we're going to negative 2 fourth root of 32 minus 7 fourth root of 162. Now for the fourth roots, let's take a look at our perfect fourth powers. So 1 to the fourth is 1, 2 to the fourth, so 2 times 2 times 2 times 2 is 16. 3 to the fourth is 81. And then 4 to the fourth, so 4 times 4 times 4 times 4 is going to give us 256. So that one's too big. So we know we're going to be working with either, well, not 1 to the fourth, that one doesn't help us because it's just a 1, but either 2 to the fourth or 3 to the fourth. Now, if we take a look at these, we have this 32 right here. You should notice that 16 goes into 32. So I'm going to go ahead and rewrite this one as the fourth root of 16 times 2. Now, the thing that will be left inside here, since we can take the fourth root 16, That'll be a 2. We're left with a 2 on the inside. So let's see if a 2 goes into 162. And it does. It goes in there 81 times, which is 3 to the 4th. So we're going to have the 4th root of 81 times 2. And the 4th root of 81 is 3. So that's what we're going to be able to take out of there. Now let's go ahead and take these out. So keep in mind here we have a negative 2. Let me change the color. A negative 2 in the front times this 2 we're taking out. We're left with the 4th root of 2. So there's a lot of 2's there. Minus 7 times taking out a 3. Left with the 4th root of 2. We simplify. Negative 2 times 2 is negative 4. 4th root of 2. Minus 7 times 3 is 21. 4th root of 2. These roots are the same, so we can go ahead and combine our coefficients. So negative 4 minus 21 is negative 25. 4th root of 2. So same thing with the 4th roots, they're just bigger numbers, and I would have your perfect 4th powers kind of written out off to the side, maybe with the cubes too. Okay, number 9. Let's introduce some variables. So this one we're given the cube root of p to the 4th q to the 7th minus the cube root of 64pq. Now we're looking at cube roots again, and if we look at our first radical here, or actually if we look at both of them together, they do not have the same radicand, so we know we can't combine them yet, but we can simplify. So remember our trick with taking out variables. You're going to take your exponent and divide it by the index. So 4 divided by 3 is 1, so we can take out 1p. We'll be left with 1 on the inside, so I'm going to leave a little space for the q and then put a p on the inside. And now 7 divided by 3 is 2, so we can take out a q squared, and the remainder is 1, so we're left with 1q. Now looking at our second group here, 64 is actually a perfect cube. 64 is the cube of 4, and p and q, the exponents aren't high enough for us to take any out. They're both less than 3, so we'll leave those. But we can take out the cube root of 64, which is 4. And we're left with the cube root of pq. Now, this one's going to look a little weird. So if you look at both of these terms, they both have a cube root of pq. Combining this one, these two terms is a little weird. So even though we have like radicals here, if you look at the terms in the front, or the coefficients, these are not like terms. So it's not like up here where we had numbers that we could just combine. These are not like terms. So what we're going to do, and you won't actually see one like this in your homework, or you shouldn't, we're going to go ahead and we know we want 1 cube root of pq. That's our goal, is to combine these into 1. The only way to do that is to have a single coefficient in parentheses where we have pq squared and then minus 4. So we're combining that into a single coefficient using parentheses. And if you think about going backwards, we could kind of distribute this in, and that would go into both of these terms, which would give us both of these. That one is a kind of weird one. Normally you'll end up with some like terms in the front. But just so you know, stuff like that is out there in case you see some other stuff while you're looking at practice problems. All right, number 10. So one with variables that will actually look a lot nicer. So this one we're given the cube root of 128 t to the 4th minus 2 square root of 72, sorry, cube root of nope, square root of 72 t cubed. Now, one thing to notice here is that we are given a cube root and a square root. Before we even do anything, we could go ahead and simplify this down, and we will do a little bit of simplifying, but we can't actually combine these because we don't have the same root. We can still simplify though, we just can't combine them. So with the 128, we're looking at a perfect cube, and so our perfect cubes, we have 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. And if we look at any of those to see if they go into 128, 64 goes into 128 twice. So we're going to have the cube root of 64 times 2, and then bring over the t to the 4th, minus, now we have 2, and this is a square root. So a perfect square that goes into 72. Remember, if you did something like 8 times 9, that works, but you'll have to go again. So try to find the largest perfect square possible, and that'll be 36. So 36 times 2 t cubed. Now let's go ahead and take things out. So the cube root of 64 is going to give us 4. And how many t's can we take out? Well, if we use our division rule, 3 goes into 4 one time, so we'll take out a t, and then we'll see what we'll be left with. Over here, the square root of 36 is 6. Leave the 2, and then again, this is an imaginary 2 out here, so 2 goes into 3 one time. So we'll take out 1 t, we're going to be left with 1. And now let's go ahead and move this guy down. So in this first one, we're taking out a 4 and a t, and now let's see what's left on the inside. We're left with a 2, and our remainder when we did 3 into 4 was 1. So we're left with a t minus, we're taking out a 6 here. We're going to multiply it by the 2 that's already in front. So I'm actually going to do that in one step. 2 times 6 is 12. And then on the in the variables, we take out 1t. So we're left with the square root of a 2. And our remainder here was also 1. So we're left with 1t. Now, for ones like these, you want to be really careful because although it looks like we could almost combine these, because one is a cube root and one is a square root, we can't go any further. So this is simplified as far as we can go. So you're not going to say that we couldn't simplify because we could simplify a little bit, but we can't combine them. So that's as far as we can go for that one. I do want to point out one thing, just so you guys are aware. If we had 4t square root of 2t minus 12t square root of 2t, so if they're both square roots, we can combine these. You would keep your like radical, so keep the square root of 2t, and then 4t minus 12t is negative 8t. So just keep that in mind. You will see ones where you can actually combine your coefficients, but this is if they both had a square root, which they did not here, which is why we couldn't combine. Okay, let's try a few more, and these are going to be a little trickier. So number 11, we're given the square root of 8/9 minus the square root of 27 over 108. Now, the first instinct you should have when it comes to fractions in radicals is to split it up. So first thing I'm going to do is split this up as the square root of 8 over the square root of 9 minus the square root of 27 over the square root of 108. After that, your instinct should be to simplify because right now there's nothing we can do. So square root of 8, and if you wanted to do these all off to the side, you totally could, and then just bring it back in. Sometimes it's a little bit cleaner to do that. but I'm going to go ahead and do it in the fraction. So 8 is a perfect square that goes into 8 is 4. So we're going to have the square root of 4 times 2 over, now the square root of 9, that's already a perfect square. So the square root of 9 is 3 minus 27. So 27, a perfect square that goes into 27 is 9. So we're going to have 9 times 3. And on the bottom here, 108, this one's a little bigger. So let's look at our perfect squares. We have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and then 36. 7 squared is 49. And then I'm going to stop there, but let's go ahead and go through the factors of 108. So we have 1 times 108, 2, so half of 108 is 54. We don't have any perfect squares right now, but we can stop as soon as we get our biggest one on the right-hand side. 3 goes into this. Now, 3 goes into 90 30 times, and this is 18 more than that, so it's going to go in 36 times because 3 goes into 18 6 times. And if we stop right there, this is going to be our largest perfect square because the numbers after this are getting smaller. So this is one kind of smart strategy you can use for finding your perfect squares. So we're going to have 3 times 36. And now let's go ahead and simplify these down. So in our first fraction here, we have the square root of 4, which is going to come out as a 2. This 9, square root of 9 is 3. And then on the bottom, the square root of 36 is 6. So that'll come out. So we're going to take a 2 out on the first fraction here. We're left with a 2. The bottom is just a 3. Minus, now over here, we can take out this 3. We're left with a 3. And on the bottom, we're taking out a 6. And we're left with a square root of 3. All right, so we're part of the way there. We still want to see if we can combine these together. And there's one thing we can do to actually simplify this down. If you look at your fractions, this first one, we have a 2, square root of 2, and 3. Nothing can be reduced there. But we can reduce this fraction over here on the right. What we're going to do is we're going to just go ahead and cancel out these square root of 3s because those are the same exact number, and we have multiplication. If it were addition, you could not do that. And we can also reduce down the 3 and the 6. One thing I will point out, though, because our goal is to add these two fractions together, or this, in this case, subtract. If I reduce this down, this is going to become a 1 and a 2. Now I'll go ahead and do it, and then I'll tell you why you shouldn't. So our first fraction is going to stay the same, and then our second fraction becomes just a 1 over 2. Well, if I'm going to go ahead and combine these fractions, we need an LCD. And what is our LCD going to be for this one? Well, the least common denominator is going to be 6. So we're actually going to end up going back to what we had, the 3 over the 6. So let's go ahead and change that 1/2 back to, we'll multiply it by 3. So we get a 3 over 6. Let's make this 3 over here into a 6. So we're going to multiply the bottom by 2 and the top by 2. Now on the top, when you multiply this 2 times 2 square root of 2, this 2 that we're multiplying it by is not in a radical. So you're going to multiply this 2 by the 2 on the outside, which gives us 4, and leave that root 2 alone. Now on the bottom, 2 times 3 is 6. You should notice that you can reduce the 4 and the 6 back to the 2 and the 3 that we started with, so we're good. Now, if we go ahead and subtract, we can get our common denominator of 6, but on the top, this one has a 4 square root of 2, this one has a 3. Because that 3 does not have a square root of 2 paired with it, we can't actually put these into a single term. We're just going to have 4 square root of 2 minus 3. kind of like what you do when you're subtracting or adding rational expressions and you have an x, except this time we have a square root of 2 that can't be combined with that 3. And now at this point, just to point something out here, we cannot reduce the 4 and the 6 because there's subtraction right here. Think of it kind of like those rational expressions, how these guys are stuck together now. Okay, number 12, couple more. This is just getting you a lot of practice. We're given the square root of 98 over 3 plus 4 square root of 2 over 3 minus square root of 2 over square root of 9. Now again, first instinct here, they're already broken up into different square roots. Let's go ahead and simplify. So the square root of 98 is another one of those that we're going to want to figure out what perfect square goes into it. And there's actually one perfect square out of our list right here that goes into it, and that is 49. So 98 is 49 times 2. Leave the 3 alone on the bottom. Plus, now this one's already simplified for us, 4 square root of 2. Leave the 3 on the bottom. Square root of 2, there's nothing we can do there. But on the bottom, the square root of 9 is 3. Now you should notice that this one is actually lining up really nicely. We have square root of 2's on the top, almost, except for this first one, which we will in a second. And we actually have 3's on the bottom, so we don't have to get common denominators. But let's go ahead and simplify this first fraction a little bit. So the square root of 49 is 7. So we're going to have 7 root 2 over 3 plus 4 square root of 2 over 3 minus square root of 2 over 3. Now, because we have common denominators, we're going to keep that 3 on the bottom and combine the top. So what we're doing in this step is we have 7 root 2 plus 4 root 2 minus root 2. And this is one of those ones where I would put that 1 in the front so that you know you're subtracting a 1 root 2. So we have 7 plus 4 is 11, minus 1 is 10 root 2. Okay, so that one worked out a little bit nicer than number 11 that we looked at. But let's go ahead and do one more. Okay. So we're on number 13. Let's actually do 2 more because number 13 is really fast, and let me show you why. So this one is 12 minus 7 root 10. Now, one really common mistake with this is that a lot of people will put 5 root 10. One big problem with this is that you combined 2 terms that are not like terms. That would be if we had 12 minus 7x. You can't combine these because this has an x and this doesn't. Well, in this one, the second term has a square root of 10, the first one doesn't. So you cannot combine them. So this is actually incorrect. So I'm going to erase that just so you don't think that's the correct answer, because this one cannot be simplified. So don't be tempted to combine those numbers in the front together. All right, now that we've done a bunch of these, I would do this one by yourself and check your answer with mine. It's a little bit trickier just because there's some more variables in here, but it's exactly the same as the others. So we have 5x cube root of xy squared minus 2 cube root of 27 x to the 4th y squared. So first thing we want to do, because we don't have like radicands, is simplify. So if we go ahead and simplify, let's go ahead and leave the 5x in the front. Now, there's no numbers here, so I'm actually just going to go ahead and there's no numbers over here either to break down because 27 is a perfect cube. So we can actually just start taking things out straight away. So let's go ahead. I'm going to do this anyway. Let's leave the 5x in the front and see what we can take out. So the cube root of x we can't do because this has an exponent less than 3. Same thing with y squared. So we can't actually do anything with those guys. So we're going to leave the cube root of xy squared alone. And now bring down the minus 2 and let's see what we can take out here. The cube root of 27 is 3. So let's bring out a 3 in the front. We can also bring out the cube root of x to the 4th. So if we can take out, or if we look at these exponents here, 3 goes into 4 one time, so we'll take out 1x. And then we're going to be left with 1x on the inside. So we'll see, and we'll put that in there in a second. But let's look at the y's really fast. So with the y's, this exponent is also too low. It's less than the 3. So we have to go ahead and leave those y's on the inside. So on the inside here, we have an x, and we have the y squared, which makes sense. That's good. That matches our other radicand over here. Now I'm going to simplify this coefficient. So we'll leave this first one alone. So 5x cube root of xy squared minus 2 times 3x is 6x cube root of xy squared. And now finally, we have like radicals, and so we can combine our coefficients. So 5x minus 6x is negative 1x, or negative x, cube root of xy squared. All right, so that's adding and subtracting radical expressions. Next time we'll see multiplying and dividing. And then we only have 2 sections left in chapter 10, and we'll be on to our last chapter.